go to that presentation till then.
Yeah.
Let me.
So hi. So yeah, hi guys. Okay, GeoGebra. Perfect. Do I already have some resources for that? Okay. Do I no module C? Okay, I don't have in module C. Fundamental pieces. Okay, no issues. I'll create one. Okay. So can we take a look at this? We have Ankit, mute yourself. Hello. Yeah. So can we take a look at here? What do we have here? We have a Cartesian plane, right? We have a Cartesian plane. We've been seeing these from our high school days. These x and y axes, right? So what we have in linear algebra is linear algebra. We start from vectors. Okay, I'm pretty sure you guys have heard the term vectors. Term vectors we first heard in physics. At least the physics students might remember those. So, what is vector? A vector is something that has a magnitude and a direction, right? So, in linear algebra, we represent points as vectors. So, the this plane, this Cartesian plane, is actually full of such points, infinitely many, in fact. So each of those vectors can be represented as, each of those points can be represented as a vector. How do we represent a vector? A vector has a line representing its magnitude and a arrowhead representing its direction. So that's how we represent a direction. So let's just plot and see a vector. I just want to see one such vector. I'll plot one of my favorite points. Okay, so this is a vector. This is how we represent a vector. This is how we represent a vector. This is one such vector. You see that the arrowhead is actually at 1 comma 2, while its tail is at origin. Very important, right? Very interesting to see that we have the arrowhead at 1 comma 2. I only gave it the input 1 comma 2 and it drew this vector with its tail at 0 comma 0. Let's see if I have another vector. What does that do? I'll take another vector. Any point of your choice, guys. Anyone? Tell me one such point that you want me to plot.
2, 3.
2, 3. Okay, let's go with 2, 3. Okay. So I have a point 2 comma 3. Oh, very interesting. Again, I'm getting a line starting from the origin, right? And the arrowhead going to 2 comma 3, right? So this is very interesting. And this is actually what we do in linear algebra. We represent points as vectors with their arrowheads lying at the point and their tail lying at the origin always. In physics, we could move those vectors around, but in linear algebra, those points are always attached to the origin. And so these vectors, they lie in some spaces, right? They lie in some spaces. Here they are lying in a R2 space, a plane R2 that has two dimensions, a length that is being represented by this x-axis and a breadth uh, that is or you can say height that is being represented by this y-axis, right? That's a plane, and we represent. So this plane has infinitely many such vectors. For convenience, when we are talking about a single point, we actually represent it as a vector. But when we are talking about infinitely many points, we talk in terms of line, plane, hyperplane. Okay, we talk in terms of that. So it's for our convenience, since it will be very hectic to draw vectors for each and every point. For our convenience, we could consider a bunch of points as points only. But singular point as vector. But those points can be represented as vectors as well. Okay. So in in linear algebra, we have two very important conditions that any vector in a vector space must fulfill. Okay, those two conditions are called vector addition and scalar multiplication. Ankit, are you here?
Yeah, I'm ready.
Yeah. Okay. Can you share your screen and can you write down those two conditions there
Yeah.
quickly? I assure you guys, I don't.
Ah, it's a,
Yeah,
it's a,
I
it's
assure you that I don't plan on wasting a lot of time on this basics. I'll quickly move on to the questions, but there are some new people, and I feel that I should just explain the basics first. So that's why I'm just quickly going through these. Okay, can you open? Yeah. So perfect, perfect. So can you just write down those two conditions: scalar multiplication and vector addition? So any vector in a vector space should must not should it must fulfill these two conditions. Okay, so just write down those vectors. So say v, if v belongs to S, that is the vector space.
uh, just two conditions, no? That
Yeah,
if V, then
if
alpha
v,
V.
no. So write down what I'm saying. If v belongs to this vector space, that is v in vector space,
If V
v
belongs
in
to a space,
to vector space, then alpha times of v will also belong to the vector space where alpha is in reals. Okay, okay. Shriram, can
Yeah,
you
yeah, one
share your
second.
screen?
Just yeah, yeah. Just get it and come. 1 second. Just a
Okay,
second.
okay. I think I should buy a graphics tablet very quickly. If you don't have anything connected, I can ask someone. Janab, uh, are you ready? Do you
Yes, yes,
have?
yes. You need
Okay.
something? Yeah. Yes.
Uh, can you can you
Just
maybe
let
share? Yeah,
just let my from my iPad.
yeah, yeah.
Just a second. I'm just setting things up. It's
Okay.
just
Any of you can share your screen. I'll be more than happy.
mm, I'm new to it, so
No
don't.
issues, no issues, Ankit, no issues, no issues. See, that's what happens when Maria is not here or Vinay is not here.
Vinay has joined.
No, no, he's actually enjoying his dinner. Okay, he's actually enjoying his dinner. I don't want to disturb him.
how do you, oh, he told you?
Yeah, yeah, I know.
Okay, wait. I'm sharing my screen 1 second.
Okay, perfect. Okay. See, guys, whatever I'm going to discuss, it might feel that I'm force feeding you these concepts. But if you want to go through these, yeah, Janab, if you're ready, you can. Okay. So if you feel that you want to go through the discussion, I have uploaded the yesterday's and the discussion that happened before that on the YouTube channel. You can get the link to that and you can watch those videos. Can you write down the two axioms, scalar multiplication and vector addition? Uh, Shriram, if you are not ready, I can ask someone else. Uh, okay, okay, just give me a second. Shriram. Okay. So yeah. So if U and V belongs to R, then U plus V must also belong to the reals, right? So R is the reals. Okay, who's this? Okay. So if U belongs to the reals, then alpha times of U must also belong to the real. R2, R2. These are not, yeah. Where alpha is in R, that means it's a constant. It's a real valued constant. By real valued, it means that from minus infinity to infinity, it can take any value. That's it. Fancy ways to say the same thing. Right. So yeah, these are the two conditions that a vector in a vector space must fulfill. Right. What happens when we combine these two conditions? What happens then? So say I have two vectors, u and v, and so say I have two vectors, u and v, and if I multiply some real valued constant with them and I add them, that should also lie in the vector space. That should also lie in the vector space. And this is also called linear combination of vectors. I'm going through these very quickly because this is something that we discussed yesterday and we spent quite a lot of time on these. So this is called a linear combination of of two vectors. I'll share my screen now and I'll show you what is a linear combination geometrically. Uh,
Should I stop? Like,
yeah, already shared my screen.
okay.
So you guys can look at these vectors, right? Let me make it more colorful. Okay, perfect. One is let's take the other one green. Perfect. Kiram, can you mute yourself?
What?
Can you mute yourself?
Can you?
Mute yourself. Mute.
Okay.
Okay. So you see here I took two vectors, 1, comma 2 and 2, comma 3. I multiplied some scalar quantity with them and I added both those vectors. Here I have this vector resultant vector. This is the result of this linear combination of these two vectors. Okay. Let me just hide it for a second. Say I multiply a times of u. This means that I have multiplied some scalar quantity with u, right? What do you think I will get when I multiply some scalar quantity with this vector? What all possible points can I reach on this vector space? What are those possible points that I can reach? Can anyone tell me? If I vary this A, what are the possible points I can reach on this R2 plane? Anyone?
All the points on the line.
Correct. So all the points that lie on the line joining 0, comma 0 and 1, comma 2 will be part of the points which or the line that I can reach with varying this A with that is associated with this vector. Let's see that. Can you see what's happening here? Let me just increase the speed for this as well. So can you see now it's visible, right? You all can see that when I vary A, I can reach all possible points in this line. That is y equals to 2x. And very curiously, this line or whatever you are seeing here, this is also called the span of the vector. Okay, what are all possible points you can reach by scaling a vector? By scaling a vector, you basically mean you're multiplying it with some real quantity. That's it. So these are all the points that you can reach by scaling this vector 1, comma 2. And this is also the span of this vector 1, comma 2. Interestingly, let's see what would be the span of the vector B. Let's see. Okay. So I have the vector V. I want to see what would be the span of this vector. I want to see that. So let me take this almost. Yeah, I think I've showed a trace. Perfect. Now, if I vary B, let's see what all possible points I can reach on this plane. Can you see, guys, what's happening here? What are we getting here? Another line, right? Yeah. Go ahead. Go ahead. Okay. So we are getting another line, right? So we can see that if we take a vector, if we multiply some real quantity with that, and if we vary that real quantity, we can reach all possible points that lie on a line being that is joining 0 comma 0 with that particular vector. So you can see that. Interestingly, let's see what happens if we add these two vectors. We took A times of u, we took B times of v. Let's see if we add them, what happens then? What can we get if we add them? So let's see. What are you observing here? Can anyone tell me? What are you observing here? What are we getting here?
A plane.
A plane, right?
Yes.
I am getting all possible vectors in every direction. And you know this, we saw that if we get a vector, we can get all the vectors in that direction just by scaling that up and down. So here we are getting the vectors in all the directions, all the directions. That means I can scale in all the direction and I can reach entire R2. Okay, this is called the span of these two vectors. And what I'm doing here, this alpha times of u plus beta times of v is actually called the linear combination of these two vectors. And where all the points that you can reach by taking the linear combination of two vectors is called the span of those two vectors. And since we had two vectors, two different vectors, we can reach the entire R2 by taking the linear combination of those two vectors. Why did I use this word different? I haven't introduced the term, but I am going to introduce it now.
Jason, your mic is off.
Okay. So what was the last thing that you guys heard?
You are going to explain why they are different.
All right. Okay. So you see that this 1 comma 2 and this 2 comma 3, they don't lie on the same line, right? That means no matter what constant I multiply with this blue vector, I can never reach this green vector. That means that they are different. They're different from one another. Let's take an example. Let's see. Let me take 2 comma 4. Sorry, my bad. Can you see this vector E? Let me just change the color for it. Let's see what happens. You can see this vector E, right? Let me just show the label for it as well. This is the vector E, and this is the vector U. This blue vector is the vector U. Let me hide vector E so that you can see the vector U. Vector U is a vector joining 1 comma 2 with 0 comma 0, and vector E is a vector that joins 2 comma 4 with 0 comma 0, and they're lying on the same line. Can you see? Now let's see, if I take the linear combination of these two vectors, what will I get? I don't know. Let's see. So this is the resultant vector I get from these two by taking the linear combination of these two. I want to see what are the possible points I can reach. That means I want to see the span of the linear combination of these two vectors. I'm interested in the span of the linear combination of these two vectors. So let's see. Let's vary our A and B and see what happens. What are we getting? Can anyone tell me what are we observing here? What is that interesting thing that we observe here? Earlier, when we took the linear combination, we were getting a plane. Okay, same is the true metaphysically as well. Which to be. So this also extends to the fact that when you have more people than required in your team, they don't contribute anything to your span. Yeah, that's true. That's true, Farad. So yeah. Anyway, so can you see what's happening here? Can anyone tell me? Farad actually pointed out a very important thing that this is what we want to observe here as well. Can anyone tell me what are we getting here? Anyone? What are we observing here?
Earlier, when the two vectors are different from each other, then there we get a plane if we take a linear combination of two. But here, since they are linear scalar multiple of each other, their linear combination is only giving me a line.
Correct. Correct. Absolutely correct. So you see that this vector that I plotted, 2, comma 4, is actually just 2 times of this vector 1, comma 2. That means this vector lies on the line y equals to 2x. In other words, this vector lies on the span of the vector 1, comma 2. Okay. And such vectors are called linearly dependent vectors. When you have a vector lying on the span of another vector, okay, that vector is linearly dependent on the other vector. In other, it's very easy to see when we have two vectors. Okay, in two vectors, it's very easy to see because you can just simply see if the other vector is the multiple of the first or not. If it is not the multiple of the first, that is linearly independent vector. You see 2, comma 3, we can never get 2, comma 3 by multiplying anything with 1, comma 2. So these two are linearly independent vectors. They even lie on different lines if you take a look at it. But these two vectors, 1, comma 2 and 2, comma 4, they lie on the same line. And hence they are linearly dependent vectors. And we also saw that since when we were scaling that vector u, we were getting a line, right? Only one line. But even when we were taking the linear combination with this vector 2, comma 4, we were again getting a line. We were not getting a plane. When we were taking the linear combination of vector 1, comma 2 with 2, comma 3, we were getting a plane. If you take a look at it, let me vary this. You see that we are getting a plane when we take the linear combination of 1, comma 2 with 2, comma 3. Because they are linearly independent, you can think of them as two separate people, two separate entities. Okay, they contribute in two different things. But say we have two people, they only know one thing. They can't. So suppose I'm creating an orchestra. I want one person who plays the violin and another one who plays the piano. I can make my team. But if I have both violinists, I can't make my team. I need another person who can play a piano. So these two vectors, 1, comma 2 and 2, comma 4, are just violinists. I can't do anything with them. They can't help me out. They can't help me out. So that's why I'm getting a straight line instead of a plane. Because 2, comma 4 is not contributing anything. Just like Farad said, that if you have more people than necessary in your team, they don't contribute anything to the team. So you can think of this 2, comma 4 as the access member of the team. Okay. So this is what we mean by the span of a vector, linear combination of a vector, the span of the linear combination of two vectors, linearly independent vectors, and linearly dependent vectors. Does anyone have any doubts till this point? Anyone? Does anyone have any doubts till this point? Okay, I think not. Okay. Ankit, can we share? Okay, Maria is here. Maria, can you share your screen? You have the
I'm
link to
ready,
the.
right? I'm already
No, no,
ready.
actually,
Oh,
Maria
okay.
was writing on the note. She has the link to the note that we were already writing on.
Oh, okay. Then okay, fine.
Yeah,
Maybe,
guys, one question for you.
Mhm.
Like, we are putting all the vectors through origin. Does it ultimately make any difference if they are put on origin or anywhere else, relatively speaking?
No, it won't make any difference.
Yeah, a reason?
We can do the same with even if they are not on origin, because we can translate a vector from one place to another place. We can
Yeah.
put like they we can just do the same thing as we are doing with origin.
but tell me, if you want a vector in R2 in some different place, will you not have to specify 2 points for that? One representing its head, another representing its tail. Will you not need the 2 points to represent a single vector?
Yeah, we need that, but the context he was asking, we
Hmm?
can just translate like a
No,
physics.
no. See,
Like in physics,
that's
we
why
can.
I told way in the very beginning that there is a difference between physics and linear algebra. The way we treat vectors in both, there's a difference between both. In linear algebra, since we are dealing with points, right? We are dealing with data. We can represent that data on graph. We can represent those points on graph as vectors. We already know that the it's PDF, Maria. It's not XOPP. I tried. I already saw it. So maybe you can leave some space. Or do you have? Okay, you don't have the link to that. Okay. Maybe we can continue anyway. We can continue, I think. So, yeah. So, Ankit, just consider this point that if you want to plot a vector anywhere on this R2, can you plot that vector with just 1 point, one single point? Can you?
One single point, and that definitely require origin.
Exactly. That's why we have the origin. That's the only reason.
Yeah. One
Oh,
more
I
thing here,
have a question
like,
here, Ajit.
one more thing here. When we
Mhm.
are what we are seeing it as linear combination.
Yeah.
Essentially, what linear combination is some sort of resultant.
Right.
Because
Correct.
what and for the resultant thing now, where relatively where the each vector is specified does not matter. Like for example,
Mhm.
uh, uh, we just wanted to see what two vectors made make.
Mhm.
Even if you make the linear combination, it is somewhere else without the beside the origin. But it is much easier for us to reconstruct that plane if they are all placed at the origin to see that.
Mhm.
That's one of the reasons that I see why we consider that origin is fixed, and we are considering all the things, these vectors, only directed from the origin because it is convenient also for us to see and argue what their resultant is, what their space is.
No, I don't think that's the reason. Because you can take anywhere. You don't
Yeah,
need. You need not have a vector that passes through the origin for that. The
yeah,
thing
but
is,
but
the
it's convenient.
very reason you have the origin constraint is because you are trying to represent points as vectors. For you to do that, you need some anchor point to represent the tail, right?
Yeah. Hmm.
So otherwise, you'll need to specify 2 points. Since you need the magnitude, you can't just say that, okay, I have this point, I'm going to represent it in any direction, because the tail actually helps you specify the direction. If you change the tail and your head is at one point, say if I am moving the tail, okay, the direction of that vector is going to change according to the tail.
Yeah.
You
Yeah.
need that origin.
Yeah. Farad, do you have any query?
Yeah, Farhad, go ahead.
So what I was saying is, doesn't it depend on the context of what we are using this for? Suppose if we were going for the distance between two vectors, right?
Mhm.
It
Right.
wouldn't matter what our choice of origin is.
Correct.
So it is a very, like, then in that case it's a subjective question. It depends
Right,
on
right.
what our context is. Sometimes it might depend, or sometimes
Yes,
it might.
right, right. In fact, we do change the vector to help us understand where
Correct.
the resultant is going to lie. Right?
Mhm.
We use the parallelogram law of vector addition for that. So
Mhm.
yeah, we do that, but that's for our convenience. And the reason we plot vectors having the tail at the origin is because you're trying to represent the vectors by only one single point in R2. So we need some anchor point for that. So that's the reason I believe that is the reason that we have vectors always anchored to the origin. Vinay, do you have any other reason for that?
Yeah, I think going back and forth between our notations and what is represented on the graph helps, right? Because
Mhm.
if you do not take the origin, I think you kind of like, if I take 1, 2, right, as the notation 1, 2 as a vector, or 1, 1, 1 here, which is there as a vector, I can visualize this directly on the graph saying, okay, this is exactly 1, 1, 1, right?
Mhm.
There's no ambiguity there. It
Correct.
kind of tells me, okay, just move one unit in X direction, 1 unit in Y direction, and 1 unit in Z direction.
Mhm.
So easily moving back and forth between the notational, whatever you use in your notations, and what is present on the graph, or the visualized vector it makes it easier that way. Maybe
Correct.
that's why mathematicians use it that way. Yeah.
Another thing, I think if we want to specify, as I was saying earlier, if you want to specify the vector in, say, anywhere in R2 except for origin, you need 2 points to represent that vector. That becomes another Achilles heel for that. Here, you are very conveniently able to represent a vector just by a single point. But there, you'll need to do extra hard work. So we'll do that. Okay, Vinay, can you share your screen? Thank God you're back.
Hmm.
Thank
Sure.
God you're back. You have the file. I was
Oh
looking for
yeah.
that file.
Yeah. Then I wouldn't. Yeah, or
Yeah,
you can write. So that's
yeah,
fine.
yeah.
I think I'll stop sharing it.
Vinay, can you continue and can take
Yeah.
over?
I
We
can.
are
I
starting
can.
from question number 17.
Sure. Sure. Sure.
Yeah, I have briefly discussed what is the linear combination, what is the linearly independent dependent vectors, what is the span of a vector or linear combination of two vectors. Briefly just went through that because we had some new people as well.
Yeah. Let me just open it.
Yeah, yeah.
Bharat, do you have any another question?
Oh, no,
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 no.
no. That
Farhad
was just
actually, let me lower his hand down.
okay. Yes.
Hi, Farad. Nice to meet you. Long time.
Yeah.
Hello, Vinay. Yeah, it's been a long time.
Hope you're doing good. Okay.
By the way, Ankit, his name is pronounced Farhad.
Farad.
No, no, no. It's Farhat actually.
Farad. Okay.
Oh, it's Farhad.
Yes.
Yeah.
Oh, I've been
I,
pronouncing your name
previous I
incorrectly.
was previous I was posted in Vivat,
Right,
which
right,
has a lot of Arabic names there.
right. Actually, I thought it was Shireen or Farhad. So,
No, no. That is Farhad. D.
right, Farhad. D.
Hmm.
Okay.
So,
I'm
have
sorry,
you
Janab, for
seen?
butchering your name.
No,
Really.
no, no. I don't
Yeah.
correct people on this generally.
It's tough for people to pronounce my surname literally.
Dhankad.
Yeah, literally. Uh,
Okay, let's continue with the question number 16. We were discussing question number 16.
Yeah.
Yeah.
Sure.
So given R3, pick any 2 points U and V in R3. Note that alpha times of U plus beta times of V, uh, where alpha and beta belong to reals, is a subspace of R3. Generalize this idea. Whenever we missed.
Yeah.
So let me just change it quickly. Okay. So we want two random points on R3. Vinay, can you continue? I'm quickly going to change it.
Yeah. No worries. No worries. Yeah. So I think we've already taken an example. But okay. Yeah. This is maybe we can start from here as well. So I've taken 2 points in R3. R3 was it? I'm sorry.
Yeah,
Yeah.
yeah.
16 was R3. Okay. So maybe I'll make it.
Question number 16, right?
Yeah. Okay. And our set would be this, and we just have to check whether it is a subspace of R3, right? That's what we have to do. So here I've
Right.
taken 2 points. I've taken U to be 1, 2, 3, and V to be 2, 4, 6. And I'm defining S. Maybe let's call it S1 itself for now. And all SIs belong to R3, right? Yeah. So SIs is all the points that are the linear combination. I'm going to use the term linear combination. I hope everyone is comfortable with it. Which means nothing but scaling the first vector and adding it to the next, the scaled version of the next vector, right? And here I've chosen alpha and beta to be my scalars, and U and V is as defined as above. So what would be S1? What would S1 be, right? Where will the points of S1 lie? Do we want to see it geometrically?
Yeah, yeah.
Sure. Or maybe just by looking at it, what is the first understanding? Where do you think it should lie?
Anyone?
I think it lie on the line since the two vectors are scalar multiple of each other. Okay, great. So he says, if I take the linear combination of U and V, I will only, I will get all the points on a line, and this line, what is this line? Is there any specific? Yeah, this line would be from 0 and passing from 1 to 3. Yeah, exactly. Okay, let's see that. So let's take GeoGebra. I hope you can all see the GeoGebra, right?
Yeah, yeah.
Is
It's
the GeoGebra visible? Okay. U is equal to 1, 2, 3, and V is equal to 2, 4, 6, right? By looking at these two vectors, right? Even visually, we can see that they lie on top of each other, right? 2, 4, 6 is passing through 1, 2, 3, and then it's being expanded after it. That's what I look at, right? And so if I take A times U plus B times V, right? And let me color this differently, orange, right? Now, if I start moving around A and B and trace it, I can see that I'll only be going along a line, right? So by this, can I say that if I take any two vectors in R3, they'll only span a line? Here I've taken U to be 1, 2, 3, and 2, 4, 6, and S1 happens to be the points on this line that we're seeing, right? Along this line is where all the points, the linear combination of U and V lie.
But what if is this going to happen for every u and v, every vector u and v?
No, if the u and v are not the scalar multiple of each other, then we would not get a line. In
Okay.
that case, we get a plane.
Okay. So can you give me an example for S2 where I will take
1, 2, 3, 4, 5, 6.
1, 2, 3 and 4, 5, 6, right? Okay. So what I'll do is I'll hide these for now and use the same v, let's call it v1 is equal to 4, 5, 6, right? That looks funny. Okay. Now this vector, if I only look at it compared to the vector 1, 2, 3, I see that it's not lying on top of each other, right? Compared to 2, 4, 6, 4, 5, 6 is somewhere else. It's not in the same direction. It's not in the same direction as 2, 4, 6, right? So now let me take the linear combination of these two, a times u plus b times v1, right? And let me color this blue and short trace. I think we've seen this before. So let me start varying. Yeah, you've seen this multiple times. I think. So what is different between u, v and v1? What is the difference between UV, the pair UV and U and V1? What is the difference that
Can
you
anyone
see?
tell us? Can anyone tell us? Pancheshwaran maybe.
U and V were actually the scalar multiple of each other, and the V1 vector is not the scalar multiple of
Awesome.
say 1, 2, 3 or 2, 4, 6.
Yeah. So can we generalize this a little bit? So let's try to see this. Let me stop these two and let's go back here. So we saw that I started with, so remember how we built our subspaces step by step? So our subspaces always started with 0, 0, 0, right? And then I add the first vector, and the first vector happens to be 1, 2, 3. And I know that when I add 1, 2, 3, I will add alpha times 1, 2, 3, right? Right? This is after adding the first vector, right? After adding u, so this is after adding u, right? I took a vector and I added it to this, and I saw that if I take the linear, okay, what is the linear combination of this one vector? Say you have u, right? What is the linear combination of this vector? You cannot, I mean, you can do alpha times u, or you can do alpha times u plus beta times u. But in the end, it's all going to be, you can make alpha and beta as just one scalar, right? You can represent it as alpha plus beta of u, right? Where
Correct.
alpha plus beta can just be some gamma, right? It's just, in the end, this is only a scalar and this is the only vector, right? So the linear combination of just one vector, right? No matter in what dimension you are, the linear combination of one vector is only a line, right? And if I take alpha equal to 0, right, that also includes 0, 0, 0, right? So after adding this set, this itself is becoming a subspace, right? This is a subspace, right? Yeah, go ahead, Jason.
So I just quickly wanted to stress on that point that you wrote here, that since we could write alpha times of u plus beta times of u as alpha plus beta times of u, right? We could write that. Say I have these points 1, comma 2, comma 3 and 2, comma 4, comma 6, right? Can I write these as alpha times of 1, comma 2, comma 3 plus beta times of 2, comma 4, comma 6? Vinay, can you write that down?
Sorry, I lost you for a second.
Yeah.
Sorry. What? Yeah.
Alpha times of 1, comma 2, comma 3 plus beta times of 2, comma 4, comma 6.
Yeah.
Now can I see that my second vector is actually the 2 times of the first vector? Can I pull out that 2 from there? Can I see 1, comma 2, comma 3 plus 2 beta times 1, comma 2, comma 3? And again, I take the alpha and 2 beta common. I get alpha plus 2 beta times, yeah, so times 1, comma 2, comma 3. Now, can you see, very interesting, that my scalars are actually written as alpha plus 2 beta. This is actually one scalar quantity. And I have reduced my two vectors as only one single vector, 1, comma 2, comma 3. Now, this shows me why I was getting a straight line there instead of a plane. Because I did not have two vectors. I only had one vector which I had scaled. That's it. Okay. So that this mathematically shows you, and we all already have seen the geometrical visualization of that in the GeoGebra. If you want, we can show it once again. So alpha times of 8 times of u plus b times of v. Can you show the span of that? W, span of w. See what are we getting here? This is actually the span of two linearly dependent vectors. Two vectors that lie on the same line, two vectors that are scalar multiples of each other. This is the span. Span is nothing but all points you can reach by just scaling a vector. Or in other words, you can manufacture. Okay. So this is the point I wanted to stress. Yeah, go ahead.
Right. So yeah, the idea I wanted to, so since we can easily see that 2, 4, 6 is just the scaled version of 1, 2, 3, this kind of makes it easy, right? So I didn't have to do all this checks to try to say that the linear combination or S1 would just lie along a line, right? I'm able to see it easily. Yeah, V is just 2 times of 1, 2, 3. So now it's easy, right? I think the harder part, I think what we've all faced, right, is when there are 3 vectors and you have to find whether the third vector is somehow a linear combination of the first two, right? And that is the type of questions we'll be facing in the next few questions, right? So given 2 vectors, I think it's pretty easy to check, right? You just have to check whether they are scalar multiples of each other. And given the third, I feel this is a good way of checking, or at least a good way of understanding whether such vectors are independent or dependent. We'll get to that. But yeah, we can just do the same thing that we did for a subspace, right? We will add the first vector to this subspace, right? And see that first we observe that this itself is a subspace, and then I try to add V, right? I try to add V, and I realize V is already present inside this. Do you agree? Because I can write this as alpha by 2 into 2, 4, 6, right? Right? So, or you can just think about it. Think about alpha values of multiples of 2, right? Alpha equal to 2, alpha equal to 4, alpha equal to 6, right? It includes all points on this line, right? So when I try to add V, right? If V already exists in the subspace, right? I initially added only U, right? And I got a subspace, and then I tried to add V, right? I tried to add V, but then V already was part of the subspace. Then it lets me know that, okay, I was already able to reach V, right? What does that mean? Since V is already inside this set, that means with U alone, I was already able to reach V, right? I didn't have to add V specifically to reach it, right? It didn't give me any new points inside the set. It was already contained inside the set, right? This will help if you think of it in this way. I think it really helps you to understand when you try to add the third vector, right? So that's why I'm trying to build on this. So try to think of when you get three vectors, try to add the first vector and make a subspace, right? And then when you try to add the second vector, see whether that vector is already part of the subspace. That's what we did here, right? We tried to add 2, 4, 6, but we realized 2, 4, 6 is already part of this, right? And then I realized, oh, 2, 4, 6, I was obviously already able to reach, right? So I can only go in one direction, which means this will be a line, right? We know that this equation is nothing but a line, right? So we can make conclusions from there. Yeah. So let's move ahead. Yeah, I think this maybe actually not move ahead yet. So in this case, we saw that when I tried to add V, it was already part of the subspace, but we realized that whatever I create, right? If I make a linear combination of alpha times U plus beta times V, it will always create a subspace. It will either be a line, or it will be a plane, or it will be the entire R3, right? So let's look at the second example to make that clear. So I think Swapnil mentioned this. So he said, let U be equal to 1, 2, 3 and V be equal to 4, 5, 6, right? So let me do the same thing that we did before. I'm going to make a set. I know 0, 0, 0 has to be part of the set, right? And then I added alpha times 1, 2, 3, right? And then I've added U here. So added U, right? And now I ask, okay, I'm going to try to add V, right? Is V already inside the subset? I'll try to find it, right? I put alpha, I need to get 4 over here. So if I put alpha equal to 4, I get 4, 4 into 2, 8, and 4 into 3 is 12. But I know 4, 5, 6, and 4, 5, 4, 8, 12 is not the same, right? So I be like, okay, this point is not exactly inside the set, right? And then we do the same thing that we did for subspaces, right? What did we do when we tried to add? Okay, so this means this is not part of this line. So let me add that. So if I want to add that, I know that I have to add all the points on that line. So that's what we did here with beta times 4, 5, 6. This is nothing but I'm adding all the points passing through 0, 0, 0 and 4, 5, 6, right? And the next thing I realize, this is not enough, right? If I take alpha times 1, 2, 3 plus beta times 4, 5, 6. This is our definition, right? We want to take the linear combination of these two vectors, right? What it gives us. But then we realize the linear combination of these two vectors spans a plane, sorry. Spans a plane, right? As we've seen before, and as we've dramatically seen here as well. Yeah, maybe in this. Okay, I'll get back to that. But yeah, we've seen that, taking these 2 points, first I said that, okay, I added 1, 2, 3, and then I realized I had to add the entire line passing through 1, 2, 3. And then I realized 4, 5, 6 is not part of this line. So I added the entire line 4, 5, 6. And then I added alpha times 1, 2, 3 plus beta times 4, 5, 6, which is nothing but all linear combinations of this. And we know this creates a plane, right? This set is a plane, and this plane passes through 0, 0, 0, right? So this also is a subspace of R3, right? This also a subspace of R3. So no matter what two vectors I take, right? And I take a set that is a linear combination of those two vectors, it will always create a subspace, right? That's why we even studied subspaces. because we wanted to understand if I took one vector and I wanted it to carry out all the properties of a vector space. A vector space property was that additive property and the scalar multiplicative property. I realized that I studied that because I want to understand all those properties are maintained, right? And then if I take the linear combination of them, it always satisfies that. That's what we're trying to say. Whenever I take a linear combination of two vectors, it always satisfies the properties of a subspace, right? So if I take any two vectors in R3, right, no matter if they lie on the same line or they lie on different lines, right, they will always create a subspace of R3. But the subspace could be different. For the first example, we saw that the subspace was a line. And for the second example, we saw the subspace was a plane, right? Okay. Any questions about this?
If there is any question until this point, you can type in the chat as well.
Yeah.
Although we have discussed these questions multiple times, for majority of people I only see Vancheshwaran who's new to the sessions. So otherwise, Anurag, do you have any doubts? Anurag,
No, no.
uh, we, get to- uh, uh, so yeah,
We'll go
we
ahead.
continue.
Yeah. So I think the important point about question number 16 was that taken any two vectors in R3, and I take the linear combination of these two vectors, right? If both the vectors happen to be zero vectors, right? If u is equal to 0, 0, 0 and v is equal to 0, 0, 0, what would the subspace be? What will be the linear combination of these two vectors? Anyone?
Just the origin 0, 0, 0.
And do you agree that that is also a subspace of R3?
Yes.
Yeah. And if it happens to be 1, 2, 3 and 2, 4, 6, we saw that we create a line passing through 0, 0, 0 and 1, 2, 3, which is also a subspace of R3. And the last thing we got is a plane, right? So I think one more thing we can realize is if we have only two vectors, the maximum we can reach is what?
A plane.
Exactly.
Yeah.
Right. So if I take linear combination of two vectors, the maximum I can span is a plane, right? And here we're talking about maximum, right? There could be places where this is not a plane but a line, right? Or it could be just a point, right? So we know examples for them, but let's move forward. I think they keep coming as the questions have all these hidden inside them. So it's nice that you all noticed that given any two vectors, the maximum we can span is a plane, right? It's a good thing to keep in the back of your mind. Yeah. The set alpha u plus beta v, where alpha and beta are real numbers and u and v are vectors, is called the linear combination of the vectors u and v. Sir is just defining the linear combination of two vectors here in this question. We can generalize this to k vectors. Observe what this set is all about, right? So he said, take two vectors u and v. If I take alpha times u plus beta times v, that is called the linear combination of vectors u and v, right? Here I took two vectors u and v. What about three vectors? That's what he wants us to do, right? 3, 4, 5, 6. Try to generalize it for more number of vectors, right? So let's see. So question number 17, right?
17, right.
So we defined a linear combination, right? And that is nothing but given linear combination for two vectors is nothing but alpha times u plus beta times v, where alpha comma beta are real numbers, right? Now let's try to go step by step. For one vector, what will it look like? What would the linear combination of one vector look like? I think we discussed this in the previous question as well. Line, right? So how do I write a line? Maybe I can just write it as alpha times u, right? As Swapnil said, this would be the linear combination of one vector, right? And this can maximum be a line. Why do I say maximum?
Because if we take a 0, 0, 0, then it would just be a point.
Yeah. If u is equal to the 0 vector, right? 0, 0, 0, then this will just be a point, right? No matter what alpha times 0, 0, 0 I take, I'll still only stay in alpha at 0, right? Sorry. Yeah. If I have two vectors, so how would it look like? We have already seen that before. Alpha u plus beta v, right? And remember alpha and beta. So for all of this, alpha, beta, gamma, or whatever A, B, C I use, all of these are scalars. And anything like U with a hat, V with a hat, W with a hat, with an arrow are all vectors, right? Yeah. So what will this be?
A line, maximum a line.
Are you sure? What about the example we saw
Oh,
about?
sorry. It should be a plane. A maximum
Exactly.
will be a plane, and
Exactly.
minimum could be a point.
Exactly, right? Because if minimum is a point, minimum is always a point where you take the two vectors to be u and v, right? If I take u to be a point, say 1, 2, 3, and v happens to already lie on the line passing through u, then I saw that it's just a line, right? Like in our example above here, 1, 2, 3, and 2, 4, 6. Here we only got a line. And in the third case that we saw is where they both were not in the same line. So then I saw that it can be an entire plane, right? Yeah. What about, how would I write it as? So I just need to do a linear combination. Linear combination is nothing but scale and add, right? So can someone tell me? Let's finish the
Alpha
first two
times
vectors.
u,
Yeah,
beta times v, and gamma times some other w.
exactly, right? Gamma times w, right? So here, what would be the maximum? What, 1 second. Yeah, sorry, I'll keep my video off for a minute. Yeah, go ahead.
A cube, 3D, anything 3D.
Yeah. So you're saying that this plane, it'll be more than this plane, right? And it's like a plane stacked over planes, right?
Right.
It can go as like a entire. So this would be R3, right? It would be the entire R3, right? It could reach all the points in R3, right?
Right.
Yeah. So this can maximum be R3, right? It can
R3.
span the entire R3. Excuse me 1 second. Yeah. So when will it be R3?
when U, V, and W all are linearly independent from each other.
But maybe we don't know what linearly independent is, but maybe from first principles, what do you feel? So what happened with just two
Like
vectors?
we can say that if U is some vector, then we have to take a V vector that does not lie on U vector, and then W vector should be that vector which does not lie on U or V.
Just on U or V, or it should not lie. So
On the linear
So
combination of
rather
these
than a
two,
line,
either.
it should be something like W is not a point on the plane spanned by these two U and V, or you take any two vectors, the third one is not on the plane spanned by the other two.
yeah,
That would be the
yeah, I think that would be a better way to put it. But maybe it's better seen with an example, right? Seeing it here like this might, scare people away. Too many alpha, beta, gammas and stuff. So we saw the example for two vectors, right? What did we see for two vectors? Two vectors was pretty simple, right? I tried to see U. I know U is going to be better than 0, 0, 0, right? Either it's going to be 0, 0, 0 itself, right? Or it's going to be better than 0, 0, 0. What is it? What do I mean by better? I'm just saying instead of being stuck at 0, 0, 0, U, if it is something other than 0, 0, 0, any other vector other than 0, 0, 0, I see that I can go to all points on that line, right? I can go through an entire line of points, right? That line has infinitely many points. And now I'm free to travel along that line how much ever I want, right? So the first vector is always new for me. It's like something, it's like, yeah, it's like saying I started jogging in a new direction today, right? I have a new direction, new path to take in the morning during my jog, right? They made a new path, and now I'm using that path because it's better than my old path, right? Now, the next vector V, if it just happens to be on the same path, right? Then I'm already going through it. So it's not like it's not like I'm going through a new path anymore, right? I'm still going in that same line that is created by you, right? But if V does not happen to be on that path, right? It's like a new diversion away from my line. Right? It's away from my line. It's not on the same line. I made a new path to myself, right? So until now, I was only sitting at home. That was my point 0, 0, 0. And then I saw U vector. And then I felt like, okay, I can go to U and back and U and back and U and back. Right? I got used to that route, right? And I'm like, okay, I'm safe in this route. And then one day my friend is like, why don't you try this new path? Right? This new path, he's telling me you can go this way also. Oh, I can go this way. What if I go a little bit this way and this, little bit this way, little bit this way and this way, right? Because I know both those directions are safe. I'm saying I can now go an entire plane, right? I can walk around this entire plane because now my friends have made me realize that, okay, both these directions are safe for me, right? It's not like I was only restricted to one direction, right? So that's what we understood from U and V, right? With just two vectors, we realized that, right? Now, how can we generalize this to this, right? How do I say, what would I say, right? I saw that, okay, I was able to do two directions. I was able to go this direction and this direction, right? This was my U direction, this was my V direction, right? If W was already on the path where I was already jogging, right? I was going jogging every day in the morning. And since my friends told me these two directions I can go freely, I went along. I traversed every single point on this. After 10 years of jogging, I'm not that old, but still, after jogging for 10 years, I've managed to cover this entire path in these two directions, right? And my friend one day comes and tells me, have you heard of this new path, right? New path that is outside both U and V, right? Which is in this direction, which is not in the direction of U and V. It's in a new direction, right? And this new direction, I'm like, oh my God, this gives me a totally new perspective. It's like, oh, I can enjoy my morning jogs much better now, right? So then I feel that, okay, I can go in these three directions freely, right? As long as he tells me a new path, I can expand my morning jog. If he doesn't tell me a new path, if he tells me some point that is already over here, W, which I was already able to reach because of these two directions. If W was already inside this, I would have already been there, right? It's like, oh, that direction. I've already been to that place before, right? I've already passed by that bagel shop, which I love eating bagels from in the morning, right? So having this new W, it's like this, right? Every new vector can either be somewhere I've already visited during my jogs or something new, right? So whatever is something I've already visited, okay, he's making too much fun of me in chat, is it? Okay. Yeah, but if it's something that I've already visited during my jogs, I'm not going to be excited. But if it's going to be something that is not on my usual route, it's going to give me a whole new direction, a whole new path to explore, then yeah. So you are now we kind of understand, uh, you know, using an example of what what it means for the vectors to be independent, right? We'll go there soon.
These two paths are part of a place, and you can think of the place as a plane, like two junctions.
Yeah, exactly. So one more thing I realized is, okay, I've got, let's say my friends were very nice, right? Chetan told me the direction U, Maria told me the direction V, and we happen to be outside of the direction, right? It made me go to an entire new place to jog around, right? And Nishant and Ankit told me that, oh, why don't we try this new direction W, right? So they've given me three directions, right? And I know, and we are in R3, right? Let's say I mean, we do live in R3, but still, let's say I'm in a game because I like being in games, right? In a game where I'm only in R3, right? So I've done my jogging in U, V, and W, all these three directions, right? All these three new planes. I've covered the entire, as you all said, that cube, right? That I've covered every point possible, right, in R3. So now, can you tell me if Swapnil comes and ask me, have you gone to this place, right? Have you visited this particular pizza shop, right? Let me call this vector
Can you
X.
scroll down and can you write down? Can you draw this after
Sure,
scroll?
sure.
Yeah, that
Yeah,
would
what do
be clearer.
you want the entire graph, is it?
Yeah, just copy it here, or maybe you can draw it again if you want.
Yeah.
Just
Okay.
copy it.
Sure.
It will be
So yeah.
visible.
So let's say this is my origin, right? This is where I initially started with. And this is the first direction that Maria gave me. This is, let me make it more fun. I hate black and white, right? Yeah. So Maria gives me this direction, right? And then I realized, oh, I can walk. I'm safe to walk here and walk back. Then the next day I walk a little bit more and walk back. And then I walk a little bit more and I walk back, right? I keep doing that. And then, okay, I try a little bit more in this direction. I mean, it's the same direction, but in the opposite direction, right? And then I see that, okay, I've successfully gone the entire path in that line, right? That's the first thing we did. Now Chetan comes with a new recommendation. He's like, there is I love dogs, so this is a pet store, right? There's a pet shop over here which you can go safely, right? So he says, why don't you try walking in this direction? I walk to it and come back one day, and then I walk a little bit more farther than it, and I come back. And I'm like, okay, I walk a little bit this much and explore a little bit more. And one day I walk a little bit this much, right? And from here I walk a little bit this much, right? And then I come back home. And then I do this all along, right? I walk in. So I see that I can walk completely in this much direction,
Yeah.
right?
Correct.
Yeah. So now I realize, okay, I've done everything, right? I've actually gone through the entire. I've gone to every place that I could using these two directions. I checked out every pet shop. I checked out every cafe, everything that I could possibly do in these two directions, right? And then Nishan and Ankit, they tell me there is this new place that is here in this direction, right? And then I'm okay. And then I try to walk from my place and I feel like, okay, this is a totally new route for me. It's not a route that I've been to. So it's like, okay, this is a totally new route for me, right? And then if that route is, if it was something that was already on this plane, I would have been like, oh, I've already visited it, right? I would have already gone to it using this path and this path, right? I would have already visited it. But this happens to be something I've not visited, right? So if it happens to be something I've not visited, and I kind of get used to it a little bit, I get used to the routes. So I go this direction, and then I go this direction, and then I go this direction, which I've been going. Then I realize, okay, I'm now able to go this entire. So initially I had a line. Let me write it. So initially I had a line, right, because of this green line. And then I added this new blue line. And then this created a plane of, sorry. Mhm.
Can you please copy that line?
Yeah, I think copying in this is little hard. I have to select the entire thing.
No, you selected the line only.
Yeah, I can't select the green alone. That's the thing. Okay. Let me draw the green over here. And copy paste. Okay. I think I have multiple of that. I'm sorry if it is not exactly parallel.
Perfect.
Yeah. So I see that, okay, now I'm able to go an entire, I can go in zigzag patterns. I can go the entire plane passing through this, right? And then this new red dot happens to be outside this, right? And I have to go in this direction to find it. And then I realize, oh, I can do the same thing that I did in each point that I visit on the red, right? I can do the same thing that I did in my first world. It's like I found a new parallel universe where I could do the same thing, but everything was different, right? Every point on this line gave me a new parallel universe where I could go through the entire plane, but the pet shop was somewhere else. The coffee shop was somewhere else. The pizza shop was something else. The taste was different. There were different human beings. I made new friends and things like that. So this is what we talk about this is what we try to understand, right? After this, if someone
Yes.
ever tells me,
Sri Vinay also met Chetan, but Chetan was having a liking for deer rather than wolves there.
okay, yeah. So after this, right? If someone gives me a fourth suggestion, right? A fourth suggestion and says, this is something new. This is definitely something new. You would have never been to this place, right? And that place is only described by x comma y comma z, right? Remember, we are in R3, right? It is only possible that it is an x comma y comma z, right? Now, this fourth vector, if I happen to have three different vectors, which is green as the first vector, blue as the second vector, and red as the third vector, and they were all three different vectors, right? New places which I did not visit before, I knew them, right? Then this fourth vector or this fourth location, right, which my friend is suggesting, there is no way I would have missed it. I would have definitely been to this location at least once. Meaning I could have reached that location already in my morning jogs, in my parallel universe job, in some parallel universe, in some job, I would have definitely visited this fourth location that they're talking about, right? So that's the power of it, right? It's like saying, if I take the fourth vector and I realize that since every time I got a new direction and I explored that direction completely, that's what I did, right? I got a new direction green and I explored it completely, right? And then I got a new direction blue and I explored it completely with green, right? I went one step in blue and I moved like infinite. I explored completely in green, and I did that for every point in blue, right? That is nothing but taking the linear combination. If you guys haven't really understood until now, I'm sorry if I've been making it too much of a story. But at each point, that's what you're doing. You're taking the linear combination of your points, right? The first vector u is the green vector. The linear combination of it is nothing but me jogging along that line. The second vector is V, is the pet store that Maria talked about. And
I
that
talked about that.
you talked about, yes, sorry. Maria gave me the first point, Chetan gave me the second point. And me reaching that point is the vector, the second vector V, and moving one step along blue and exploring completely along the line of green is nothing but the linear combination of U and V, right? It's like saying keep beta constant and vary alpha, right? If I was alpha times green plus beta times blue, I'm sorry if that's confusing. 1 second. Yeah. So moving one step along blue is nothing but keeping beta is equal to some constant and vary alpha, right? That's what it means. Me exploring this entire direction, green direction, on each point of blue is nothing but taking the linear combination of these 2 points, right? And the same thing happens for red, right? I can do the same thing for red. Whatever I did for these 2 things, I'll do it for every point on red. That is nothing but alpha times green plus beta times blue plus gamma times red, right? So we've seen this before. Alpha times green plus beta times blue is this entire plane, right? And if I do that entire plane for every point on red, right, that will make this entire R3, right? I'll be able to reach the entire R3, right? Only if green, blue, and red are different, right? Green is a new spot for me, blue is a new spot for me, red is a new spot for me, right? And any fourth vector, let's say that fourth vector is black, right? Right? This is the fourth vector. This black will always lie within this because black is in R3, right? So the fourth vector, if I'm already given 3 new vectors, 3 new dimensions for me to explore, if I've already explored every point of it, this fourth vector would have already been explored by me, right? So that's something we have to I think that's something we learn as we keep going, right? We can generalize this for k vectors, right? So there could be the case that the first spot, okay, let's. So we saw examples of.
Colors example is easier to understand than the roads because like you know that you take 250 like you take the 3 primary colors and you take them to the maximum extent you get the color black, right?
Oh
So
yeah.
like yeah.
Oh, that's really nice. Okay, I didn't even realize that. I was not even thinking about
Yeah,
RBG.
yeah, you did that, yeah.
Okay, okay. Wow. Oh, that's really nice. I think what Maria said is, see, if I've given only the color green, right, and I can change the intensity of it with alpha, right? I can change the intensity of this green, right? I can have all colors from light green to dark green and like stuff like that, right? But I can never reach orange or yellow or red or anything in that sense, right? So only if I'm given the new color red, if I'm given light green, okay, let's say I'm given light green or dark green, right? Dark green, right? This will not amount to much, right? Alpha or alpha 1, alpha 2, right? This would have already been covered by this, right? I would have already taken some alpha value, which alpha value of G which would have given me dark green, right? So only if that color is unique, right? If it happens to be alpha 2 times red, right? Now I know I can change green's intensity and red intensity, and I can get different colors between red and green. Maybe I can even show that, right? I get a different color. I don't even know what the color is. I'm sorry.
There was one day you weren't there where I used this example where like red and purple were two independent colors and you got purple. And one day I showed that if you use a different shade, you'll get light purple. So it's like the different shades of purple are like in a similar plane or line or something. And then, yeah.
That's very nice. Okay. Maybe I'm not very.
Yeah, dude, I didn't know, but yeah, yeah, this is some like, and also the thing is that we can think of black as R3 because if you take like, I think if you take a maximum value you can take it's like if you take 255 of green, 255 of red, and you will get black, right? So you
Yeah.
can think of black as R3.
Yeah, that's right. So I think, yeah, in the end, I could have taken vectors u and v such that v already lies in the span created by u, right? But if it happens to be outside that span, right? If it happens to be in the same span, I mean, then you don't really expand it, right? You're still in the same direction. But if it happens that it creates a new direction, right? It can become a plane, right? I mean, I think the bigger idea is that after you take three different directions, right? All your other vectors, x vector, y vector, z vector, whatever you take, it's already inside this space, right? That's the most important part, I think we have to understand. Yeah. So, yeah, for now, maybe we'll move on and see what questions we have. Where were we? 17 questions were done, right? At each point, each vector is telling you how much, I mean, alpha times u is telling you how much to move in the direction of u, right? That is one more thing you can think of. U is a direction, u is a vector in a particular direction, and alpha times u is telling you how much to move in the direction of u. So alpha times green plus beta times blue is nothing but how much should I move in the green direction and how much should I move in the blue direction, right? That is also an important point you can have in your mind. Yeah. Okay. So question number 18. We say that a vector W is manufactured by U and V if W belongs to alpha times U plus beta times V, right? Okay. This is quite simple because we've already talked about it. So we're going to use the term, sorry, W is manufactured, yeah. W is manufactured U and V if W belongs to the set alpha U plus beta V, right? This is what it says. So this is pretty simple now to think about, it, right? This is like saying Nishan gave me a new recommendation, but I realized I've already been to that recommendation, right? I've already been to the he told me that there's a sports shop, right? Which is exactly at 1.27 comma 3 point. Okay, maybe that example will be quite hard for me to reach, but let's say 1 comma 3 comma 5, right? But I've already been to all the directions in U and V, so I've already been to 0.5.
Example, yeah, in the example you took, like you went to the pet store and the sports store was actually in the way when you went to the pet store. So it's not anything new that you discovered. Yeah.
Exactly. Yeah. So let's say this, just to make it simple. I know this is not very pleasing, but I can see that this is a new direction. This is a new direction. This was Maria's, or this was the green. This was the green dot that I visited, and I explored every point on that line. Then this is the blue area, which is told by Chetan. And I realize that this part, right, this 135, I've already visited by exploring Maria and Chetan's directions, right? I go 1 unit in the direction of Maria's direction, and 1 unit in the direction of Chetan's direction, right? I will land up at 135, right? And I'm hoping that's right. Yeah. Oh, shoot, that's not. My bad. So this has to be a 3 for me, things to be easier for me. But yeah, I think you kind of understand, right? Since these two are different directions, right? I know that it'll create a plane, right? This creates a plane, right? Because I can clearly see C is not a scalar multiple of M, right? Blue is not a scalar multiple of M. I see that, okay, it's a plane. And then I look at the third one and I'm like, okay, since it is already a point that I was able to reach by this linear combination, 135 already belongs to some alpha times U plus beta times V. So I can say W can be manufactured by the vectors U and V, right? So Nishan's point, the black point, can be manufactured by Chetan's point and Maria's point. That's what we kind of understand from this, right? Awesome. So his recommendation was, I feel we should update our recommendation system. Nishan is already in sleep mode. So now we know why we are lacking. Please, Lester, I'm so sorry for waking up. I'm sorry. I was just trying to make a small joke. Sorry if I woke you up. So
I was
thanks
not
for the
sleeping.
I
great.
know, he's like, what's happening?
No,
Well,
I was
suddenly
not
he heard
sleeping.
a snake.
No, I was not sleeping, man. I was all ears, I was just trying to relax my eyes. That's all.
Yeah, please do.
He was meditating.
Yeah, he was thinking of a new recommendation to give for me. So
He was jogging
keep
in a
trying hard.
parallel universe.
Jogging in a parallel universe. Yeah. Go ahead. Okay.
No,
It's like my father says, like, I'm not sleeping, I just close my eyes. I know the difference.
I think he was putting efforts to see the hyperplane in 4-dimensional and some higher dimensions.
Hyperplane.
Okay. Is it okay if we go for the next one as well?
Yeah, we can go to the next question.
I guess Ankit was not there yesterday, no?
No,
Yeah,
I
he
was
wasn't
not.
there. Maria wasn't there
was
either.
I left early too, yeah. I fell asleep actually. I didn't realize I fell asleep
So
until
Ankit was there, right?
No, I was not there.
No, no,
So
he wasn't there.
I
Then
was
it's
in Kuwait,
fine. Then it's
and
fine. I thought that
there was no
they
Wi-Fi.
got me for hyperplanes. Anyways, just a small joke.
Okay.
Okay. So can we go to the 19th question?
Yeah.
Okay. Show that 1, 2, 3, and 4, 5, 6 can manufacture 7, 8, 9. Also, 4, 5, 6 and 7, 8, 9 can manufacture 1, 2, 3. Right? And 4, 5, 6 can be manufactured by the other
Linear
two.
combination.
Yeah. So let's go with, yeah. So manufactured in the sense is equal to the linear combination. That's what we saw, which is nothing but saying, so we have three vectors. Let's say question number 18. We have three vectors. Vector 1, right, is equal to 1, 2, 3. Vector 2 is equal to 4, 5, 6. Vector 3 is equal to 7, 8, 9. Let's start with our usual. So, okay, our first goal, right? So this is our goal. Our goal is to show 7, 8, 9 or V3 can be manufactured by V1 and V2, right? So what do I have to check? I have to check whether 7, 8, 9, right, belongs to the set of alpha times 1, 2, 3 plus beta times 4, 5, 6. Right? This is nothing. I'm just writing this down from the definition that we gave up below. Right? We say the vector W is manufactured by U and V if W belongs to that set, and the set includes the linear combination of the first of the vectors it is being manufactured by. Right? So they want us to show that 7, 8, 9 can, sorry, 1, 2, 3, and 4, 5, 6 can manufacture 7, 8, 9. Right? So 7, 8, 9 should belong to the the points of all linear combinations are 1, 2, 3, and 4, 5, 6. How do we show this?
We can easily show this using GeoGebra.
Perfect, perfect. So let's go to the easier visualized way, right? So let me write this as V1, right? V2, 3, 4, 5, 6. Why can't I write V1 here? Okay, 8. 1, 2, 3, 4, 5, 6. And 8. Yeah, and V3 is equal to 7, 8, 9. Okay. So what is the first thing we observe? Just by plotting these three vectors on this plane, what is the first thing that we observe?
They are all lying on the same plane.
I really can't see that. But what is the easier thing to observe? Is anything a
They're
scalar
not on the
multiple
line.
of the other? Yes. Nothing is a scalar multiple of the other, right? No two vectors are lying on top of each other. Can you see that? We saw for the vector 2, 2, 4, 6, you can see this, right? Clearly, you can see that 2, 4, 6 is lying on top of 1, 2, 3, right? But for these three vectors, I can clearly see that they are not on top of each other. Visually, at least. Maybe I'm not trying to, expand this to what we know, but you can clearly see that it's not. So I can actually do that easily as well, right? Take V1 and V2. Can V2 be expressed as some alpha times V1? It
It's
cannot.
not a multiple.
right? We can clearly see each vector is never not a multiple of the other, right? No matter what two vectors I take, right? I think it's easier, clearly seen on the plane rather than trying to do the mathematical thing, right? Trying to show that they cannot be expressed. So I can see that, okay, no two vectors are lying on top of each other. What does this tell me? It tells me if I take the first vector, if I take Maria's suggestion and start walking along this direction, right? Right? If I start walking along this direction, I will have an entire line to walk around, right? So right, this entire line, let me make it green as well. Right, this entire green line I can walk along, right? And I can do this for any vector I start with, because that's what we said, right? Any first vector we take, we know that it's going to give me a new place because I've never visited any place. The first suggestion that my friend gives me, I can always go in that direction and I can explore it, right? Now, and I can safely take any of the two other vectors now, right? Why am I saying that? Because none of them are on this line, right? We saw that none of it is a scaled version of the other, right? So now let me start taking, I know that it creates a plane if I take the linear combination of two vectors, right? And it happens that those two vectors are not a scalar multiple of the other, right? So now I have a plane passing through 0, 0, 0, v1 and v2. I forgot how to go. Shoot.
What happened, Vinay?
How to go underscript? I forgot.
Underscore. Okay. Shift and underscore from
Yeah, I
backspace.
just did it.
Two
I don't know
buttons.
why I forgot. Okay.
No, that's near to this
Two
shift
buttons left to backspace. Two
Underscore,
button left to
underscore.
backspace. Yeah.
Okay. Right. And now I am saying I'm going to go along v1 and v2, which means the new suggestion that Chetan gave me, right? I'm not seen this third vector yet. I've not seen the third suggestion. My second suggestion that Chetan gives me, since it is not on this green line, right? The first green line that Maria told me, now I know I can go to any point on this, I can go to any point on this plane, right? By moving in the direction that Chetan gave me and moving along the line that Maria first introduced me to, right? And I get this entire plane, right? Now, the third vector from this part, it becomes a little tricky to understand. 789 did not lie on 456, right? It was not a multiple of 456. 789 did not lie on 1, 2, 3. But 789 does lie on the plane that can be reached by 1, 2, 3, and 4, 5, 6. So now I can clearly say that 789 can be manufactured by 4, 5, 6, and 1, 2, 3. Because it is some linear combination of 4, 5, 6, and 1, 2, 3. Right? Maybe I can also try to find that. I went 1, 8, 9, 1. Okay. And this is my target vector. Let me make it orange. The black vector is what I'm moving, right? Can someone tell me what values of So 2 and -1, right?
Yeah.
Yeah, I think I'm very close myself. Yeah. So now I can see that I've reached exactly over the orange line, right? When b is equal to 2, which means I go 2 times in the direction of 4, 5, 6. Chetan gave me a direction and I'm going to go 2 times in that direction, right? And I'm going to go -1 times in the direction of 1, 2, 3, right? A is equal to -1. So I'm going to go in the opposite direction that Maria gave me. It's a same direction, but in the negative side, which is along this line. And then I'm going to go in the direction that Chetan gave me 2 times, right? Two times that value. So I can see that I can manufacture this vector 7, 8, 9, which means I've already been to that pet store. So bad recommendation. Yeah. Okay. So we saw that we can manufacture 7, 8, 9 using 1, 2, 3, and 4, 5, 6, right? So we were able to represent it as 7, 8, 9 is equal to 7, 8, 9 is equal to -1 times 1, 2, 3 plus 2 times 4, 5, 6. Right? We saw this in GeoGebra. Now, what if I started taking the suggestion of with Chetan's, or maybe I started with Nishant's suggestion first, right? So this is my first suggestion, right? So Nishant gave me the suggestion, go to this place 7, 8, 9, right? So since this is my first suggestion, right? Let me duplicate this. So now 3, right? So this entire line was what I could go through, right? Similar to how I could go through in Maria's direction. Since I'm taking Nishant's suggestion first, I see that, okay, I can create this entire line, right? Now the second suggestion that I get is Chetan's suggestion. And now I can create a plane which is passing through 0, 0, 0, and V3, which is Nishant's suggestion, and V2, which is Chetan's suggestion. So this again created a plane, right? Right. The first thing I created was this line. I could go along this line. And the second thing with Chetan's suggestion, I could create this plane, right? And now I try to see the third suggestion. And I'm like, okay, wait. This suggestion also lies on the same plane. What does this mean? Anyone? What does this mean? Do you agree that we can manufacture Maria's suggestion using Chetan's suggestion and Nishant's suggestion?
Yes.
Yeah. Right. So I may have changed the order of taking the suggestions, right? But in the end, I was always able to cover the third suggestion before, in the first 2 suggestions itself, which means the third vector that I take between these 3 suggestions, right? Since I would have already gone to 7, 8, 9 if I took the suggestion of Maria and Chetan, right? I was already able to reach this entire plane. And since 7, 8, 9 is already on that plane, I would have already reached it before, right? Because of exploring it continuously, right? The same case can also go if I had taken the suggestions in a different way. I took Nishant's suggestion and I took Chetan's suggestion, right? I explored it completely. And then the third was already, it kind of got covered with the first 2 suggestions. So can you see that I can manufacture 1, 2, 3 with V2 and V3 as well, right? Which is nothing but saying, if I take A times V3 plus B times V2, which is nothing but saying linear combination of Nishant's suggestion and Chetan's suggestion, is this black vector, right? And I want to reach, Oh, I've already reached it, is it? That's not, that doesn't make sense. This. Oh, okay. 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 Let me make this 1 and 1 for now. 1. Yeah. So this black vector is what is manufactured by Chetan's solution and Nishan's solution. And by varying A, right, I can get closer and closer to yeah. And there I have reached that green point. The black vector is on top of the green vector, right? Let me hide it and unhide it. It's the exact same vector, 1, 2, 3, right? So I was able to manufacture 1, 2, 3 using 4, 5, 6, and 7, 8, 9, right? And similarly, you can think about the third way, right? I would have taken Maria's suggestion first and then taken Nishan's suggestion second. And then I would have realized I already completed looking at Chetan's suggestion, right? So you can represent Chetan's suggestion as some linear combination of 1, 2, 3, and 7, 8, 9. Right here also alpha and beta happen to be -1 and 2. So in the second case, we were able to show that what suggestion did we try to explore? 1, 2, 3 is equal to 1, 2, 3 is equal to, sorry, -1 times -1 times 7, 8, 9 plus 2 times 4, 5, 6. Right? This is V1. This is V3. Maybe I'll write it in colors as well. Okay. And this is V2, right? This is green. This is orange. This is red, right? This is what we saw over here as well. So in a similar way, you can also find it for the last one, like 4, 5, 6. What will 4, 5, 6 be equal to? Can you now try to find it in your own way? So you should express it as some combination of 1, 2, 3 and 7, 8, 9. So how would you represent 4, 5, 6 as? So can you fill in this alpha and beta values?
Half of 0.5.
Sorry, I couldn't hear you.
Can you repeat that?
0.5.
1 by 2 and
Nice.
1 by 2.
That's nice. So he says, so if I take alpha comma beta is equal to 0.5, I get 0.5 comma 1 comma 1.5, right? Sorry, 1.5 plus 3.5, 4, 4.5, right? And this will give me 4 comma 5 comma 6, right? Let me ask you this question as well. Is this the only values of alpha and beta that satisfy this equation?
Are these the only two values?
Yeah, I think.
And why?
Actually, I'm going like mathematical way. So like the first
Okay.
equation is 1, 2, 3 and
No more. Let's think about it intuitively, right? So for -1 comma 2, I got, so okay. So -1 times 7, 8, 9 plus 2
yeah,
times
I get it.
for
Actually,
each
Ankit, so
chain.
the other day.
Yeah. For each change in this, you're actually going to reach a new point on that plane, right? You're going to reach a new point on that plane. Think about this. When I was showing you this, right? I'm sorry if it's very messed up right now, but initially I had an entire line, right? And when I got the new direction, right? When I changed B a little bit, which is when I jumped from here to here, right? I got to entirely new point in the line, and then I started going along this green line, right? So that means I made my beta some constant, right? Let's say let's say initially the beta constant was 1, and I added 1 to it. So I jumped from here to here.
Yeah, it's like if we take a Cartesian plane and we want to go to the 4, 5, then the only way to go that point is go 4 times in the direction of x and 5 times in the direction of y.
Yeah, I think Swapnil has explained it much better than me. Thank you so much. That's a very nice explanation. Exactly. Just like how you look at the Cartesian plane, right? If you want to go to a specific point on the Cartesian plane, right? And you want to use it by moving x comma y, right? X comma y is telling you how much to move in x direction and how much to move in y direction. If I want to reach the point 2, 3, I have to move 2 units in the direction of x. And then I have to move 3 units in the direction of y, which is nothing but 3 times, which is nothing but saying 2 times in the direction of 1, 0 plus 3 times in the direction of 0, 1. This is nothing but I cap and j cap. So maybe this is what we study, right? This is another way of writing the vector 2, 3, right? So this alpha beta value is unique, right? There's only a unique alpha beta value that can reach, but that is only the case of these 3 vectors. There could be cases where, yeah, we'll see the cases later. I think for this case, it's quite clear, right? We're able to see that all 3 vectors are not on top of each other. That's the first thing that we noticed. When we came over here, the first thing that we noticed is vector 1, vector 2, vector 3. Let me get this back to point -1. Yeah. Yeah. So these 3 vectors, first thing we notice is they don't lie on top of each other. That's the first thing we notice. So I could always take 2 vectors and I know I will get a plane, right? And when we tried to see the third vector, we saw that it always lied on that plane, right? Which means I can manufacture the third vector given any 2 vectors on that plane, right? That's what we kind of want to generalize. If I take any 2 vectors on that plane, I can show the third vector on that plane using a linear combination of the first 2. That's what I did. When I took 1, 2, 3, and 4, 5, 6, I created a plane. And then I could show 7, 8, 9, which lies on that plane as a linear combination of 1, 2, 3, and 4, 5, 6. And that linear combination was unique. Alpha, beta was unique, right? That's what we saw. This can also be kind of, how do I say, related to the similar sense of R2, right? When I take 2 vectors in R2, and those 2 vectors do not happen to be a scalar multiple of each other. What does that mean? It means they will span the entire R2.
Yeah, yes.
Then if I take any third vector on R2, I can obviously define it as some linear combination of the first 2, right? because I know the first two spans the entire plane. That is what is happening here, but in a higher dimension on a smaller plane. That is the same thing that is happening here, right? It's like this point is just another point on R2, and these two vectors are like spanning the entire R2. So you can obviously show that third point, which is in R2, as a linear combination of the first two. But the best part is, if I take the first two and take the linear combination of it, I can show it as a third vector. If I take the third and second, I can show it as a linear combination of the first. I can do it for any case. Yeah, Chetan, you wanted to say something? Okay.
Continue.
Yeah. Okay. So question number 20. Can 210 and 308 manufacture 111?
Can they?
Do we want to see this on the graph as
Yeah.
well?
Yeah, maybe we can take two knobs, change the knobs. Let's see.
Oh, so you don't want to make the plane, is it? I thought that we
Yeah,
can make the plane and then check whether it lies on that plane, right? That's
yeah,
the
we can do
good.
that as well.
Since we understand now that
Mhm.
if the first two vectors are not lying on top of each other or are not scalar multiples of each other, they make a plane, right? Yeah. So let me share this with you guys if you guys want to play around with it later. This is question 19, right? Yeah. Okay. Let me make a new one. Okay, so we have our first vector to be 208, am I right? 210, sorry. My bad. 210, and v is equal to
308.
308. Thank you so much. And can we see it clearly that they are not scalar multiples of each other?
Yeah.
So can we safely say that this will create a plane? The linear combination of these two vectors will create a plane. So what I will do is make a plane passing through 0, 0, 0, u and v. Right? So we know this is the span, or this is the linear combination. All these points on this plane can be manufactured by vectors u and v, right? Now we want to check for the vector w, which is 1, 1, 1, and check whether this vector 1, 1, 1 lies on this plane, right? So can you see the green vector over here? Can we see that? Can we say something about it? Is it on that plane or is it not on that plane? Anyone? Can I manufacture 111?
What do you guys think? Vanchishwaran says no, that you cannot.
Exactly, you cannot. Why?
The condition is it must lie on the plane.
Exactly.
True.
Exactly. The green vector, if I want to be able to manufacture it, it should lie on that plane. Why? Because the plane tells you all those points that can be manufactured by u and v. By manufacture, we mean all the points that are the linear combination of u and v, right? Since it is not on that plane, you cannot express it as a linear combination of u and v, right? Okay. What about question number 21?
No, they cannot manufacture. Because the plane we get by using 001 and 011, 101, 100 would not lie on that plane.
Can you elaborate a bit more? Maybe it's not quite clear to me why. I mean, I would have checked on GeoGebra to make sure. But how are you able to say it perfectly? Maybe you can tell others so that they can also understand.
Can anyone else?
No, I want Swapnil to
Like
elaborate.
if you take a linear combination of these two, then the answer, the generalized version you can get is 0, alpha, and beta.
Awesome.
And you cannot manufacture one.
Exactly. Right. What he's saying is just by looking at the vectors, right? Vector v1 is equal to 1 0 0 or 0 0. Okay, 0 comma 0 comma 1. Right? v2 is equal to 0 comma 1 comma 0. Right? And v3 is equal to 0 comma, sorry, my bad, 1 comma 0 comma 0. Right? If I take the linear combination of v1 and v2, what will it look like? It will look like alpha times 0 comma 0 comma 1 plus beta times 0 comma 1 comma 0. And I have to somehow see whether v3 belongs to the set, right? Does it belong to the set, right? We have to check that. We have to check whether it belongs to the set. But what is v3? v3 is 1 comma 0 comma 0, and we want to check whether it is, if it belongs in 0 comma beta comma alpha, right? Can I write this entire thing as 0 comma beta comma alpha?
Can we?
What if I take alpha comma alpha is equal to 2 and beta is equal to 3? What happens? This becomes 2 times 0 comma 0 comma 1 plus 3 times 0 comma 1 comma 0, which is nothing but 0 comma 0 comma 2 plus 0 comma 3 comma 0, which is nothing but 0 comma 3 comma 2, correct? And this is nothing but 0 comma 3 comma 2, right? We can see that these two are equal, right? So I can write it like this, right? But realize that whatever value of b, now you want to find that beta and alpha, which gives me 1 comma 0 comma 0, right? But you realize how much ever I change beta and alpha, it will never affect this direction, right? So this is not possible, right? And obviously we can do the same thing and visualize it, or even without using GeoGebra, right? What is this? This is nothing but the plane passing through
Plane x, y, say.
y and z coordinate,
Yeah.
right?
Yeah.
And this is a point on the x coordinate.
Perpendicular to the plane.
Exactly. So that plane would be something over here. If I take this as the z coordinate, this as the y coordinate, this as the z coordinate, and this as the x coordinate. So this would be that point, right? This should be that point I want to find. But I know the linear combination of these two can only span this plane, right? So this will not lie on the plane, right? Very good that Swapnil was able to say this very early on. That's really nice. Let's move ahead. So we can clearly see that 1, 0, 0, 0, 0 cannot be manufactured by 0, 0, 1 and 1, 0, 1, 0. So can we now talk about when can two vectors in R3 manufacture a given third vector?
Only when the third vector lie on the plane generated by those two vectors.
Okay, a good start. But it's not perfect yet. Why do I say it's not perfect yet?
Panchashuran says that all three must lie on the same plane.
I feel it's right, but it's not complete.
It must be a linear combination. To be a linear combination, it must lie on the same plane.
But why do we think that we will always create a plane? Are we assured that we will always create a plane? What if my
We
three
can say
vectors are,
the linear combination of those two vectors should produce the third vector, and the linear combination can be a line, a plane, and
exactly.
it should be
That is a
outside
more
from that.
complete, exactly. That's a more complete, perfect answer, right? Why do I say that? Let's see. Okay. So you said that the third vector should lie on the plane. Right, formed by first and second, right? But what if first and second does not even form a plane? Can you give me an example of this? Very simple example. V1, V2, V3. Can you give me an example?
Example for when it does not form a plane.
Yeah.
1, 2, 3, and 2, 4, and 6.
Awesome. Right? Do you see this? What does the linear combination of 1, 2, 3, and 2, 4, 6 make? It only makes a line, right? Now you cannot say the third vector has to lie on a plane because there's no plane for it to lie on. It should only lie on that line, right? What if this vector was 3, 6, 9?
Then it would lie on that line since it is a.
Exactly. This would also lie on this line. So this vector lied on the line created by so this created this, right? I created this using the first vector. The second vector also lied on that line. The third vector also lied on that line. So I can say that vector 2 is also dependent on vector 1. Vector 3 is also dependent on vector 1. And I can go the other way around as well. Vector 1 is also dependent on vector 2. Vector 3 is also dependent on vector 2. I can do the other way around. Vector 2 is dependent on vector 3. Vector 1 is dependent on vector 2. It can happen in any way, right? Because all of them lie on the same line. In whatever order I take, they all lie on the same line, right? So how would you, I think Swapnil has understood it completely. So how would you, if you have understood what Swapnil said, how would you restate this statement to make it cover these kind of vectors as well? So you cannot use this plane here, right? So how would you generalize the statement? When can two vectors in R3 manufacture a given third vector?
Is the question for me?
Yeah,
Answer?
you can go ahead if I'd be happy if you can answer. No pressure, it's fine. Think about how we expanded our subspace. I think that will guide you towards the answer. The reason I made you think of this as a subspace expansion is so that you can understand this concept very well, right? No matter what vector I put in, 1, 2, 3, this creates alpha times 1, 2, 3. When I take the second vector, it happened to lie on that
Okay.
subspace.
Yes, yes.
It lies. So this is how I would state it. If the third vector lies on the subspace, why subspace? Because we know linear combination of two vectors could either be a point or be a line or be a plane. We don't want to restrict it to say that it
just
lies on the plane. Exactly.
Okay.
We will say, since subspace includes all the points as well as lines as well as planes, if the third vector lies on the subspace created or manufactured, let me use the word manufactured by the first and second vectors, then the third vector can be manufactured by V1 and V2. Let me call them V1, V2, first vector and second vector. Or maybe I can make this better. If E3 lies on the subspace manufactured by V1 and V2, then V3 can be manufactured by V1 and V2, right? And by manufactured, it means linear combination.
Linear combination, yes.
Remember, linear combination creates a subspace. The subspace could be a point, a line, or a plane in the sense of R3. And with just two vectors, it could be the entire R3 if there were three vectors. We saw that also. Right? Since we have only two vectors, it can maximum create a subspace of a plane. And if V3 happens to lie on that subspace, then we can say that it can be manufactured by V1 and V2.
Yes.
Right?
Right.
So I will mark this as important when you guys are going through your notes. Right? Okay, awesome. When can two vectors in R3 fail to manufacture a given third vector?
When it does not lie on that linear combination.
Exactly. Right, very similar to this. Maybe I'll just copy paste this because I'm lazy. So this is question number 23. V3 Yeah, if V3 does not lie on the subspace manufactured by V1 and V2, then V3 cannot. Right? Cannot be manufactured by V1 and V2. Right? This is the only difference between 22 and 23. Awesome. What's the time? 11:38. Is it okay if we go for 24 minutes? 20 more minutes?
I think we can wrap up now. And we'll continue discussing the equations. Officially, we can wrap up now.
Awesome. Okay. I think we did quite some.
Yeah.
I think 24 and 25 is very close to what I mean. We can finally forget about manufacture and all that, and talk about linearly independent and linearly dependent sets.
Let me stop the recording.
Sure.